Hi, good morning. This is going to be 18th lecture on topology, hopefully a very short one. The reason is I just would like to point out some few facts, 3 or 4 simple facts about dense subsets. None of them are very important. Okay, in fact, most of them can be left as exercises. But then the reason why I want to do them is if you go through these small things, okay, observations, and you will gain mastery over the subject and you will be very confident about the notion of dense subsets. That's the main reason. I hope you appreciate that. Okay, let's get started. I forgot to write references. That's as usual. Okay, right. So in the last lecture, you may recall if D is a dense subset of X and F and G are continuous real valued functions. It could be more than that, but let's may not worry about. And these are all continuous, both are continuous. And assume, okay, for all x in D, fx equal to gx. That is, f and g agree on the dense subset. Then what is the conclusion? F equal to g. Okay. Notice that in the entire mathematics, in all of mathematics, you will see lots of such results. They are all scattered, and the teachers do not try to bring them and show there is a unifying theme in all these things. Okay, and I would like to point this out, even though that's not exactly pertinent to topology, but as I said, I always deal with mathematics, not only single subject. Okay, so let us just very quick recall for those students who are not been trained to do like this. It will be useful. But you have been trained well, of course you can skip this if you want. Suppose x and y are sets, right, and f and g are functions from x to y. Then when do I say f equal to g? See, some teachers write f is identically equal to g, but one doesn't say that. As function they are equal. When that is if and only if for every x, okay, in capital X, we should have fx equal to gx, right? So if I want to check two functions are equal, I have to check that they take the same value at each and every point. That's what it means, right? So I have to do a lot of checking in principle. Do you agree with that? Okay. Then, so when do I say f is not equal to g? Then again it's not needed, but let me see. That means if only if for every x something must be true. Therefore, if it is false, that means there exists an x in capital X, that fx is not equal to gx. Okay, right. To show functions are not equal, it's easy. I only have to find one single point and say f and g take different values, right? Okay, right. So most often, in lot of time we have to check whether the functions are equal. Let us look at the simplest case to start with. Okay, so if f and g are real valued functions and continuous, then we saw if f equal to g on q, the set of rationals, or on r minus q, then we saw f is g on r. Okay, this is a special case of what we did about dense subsets. Okay, right. And why it's significant is what I want to say. Now suppose I have two linear maps f from v to w. Okay, I assume that v is finite dimensional for the sake of it, and let b equal to a basis. v1 to vn is a basis of v. Okay, these are linear maps, right? Again, notice that, okay, if these are all vector spaces over an infinite field, for example over R, then the number of elements in V will be infinite unless V is zero space, right? Even if it's one dimensional, there is going to be infinite number of elements. V will be an infinite set, right? So to check f and g are equal, I have to check f and fx equal to gx for each and every x in V, right? But if with additional assumption, namely f and g are not any function but they are linear maps, that means if I know fvi equal to gvi for all I, okay, then I know f is g. You see that? Now I reduce to checking only finitely many points. Yeah, f and g take value, same values at finitely many points, namely this each at each and every vector in the basis, in some basis. Even if one basis I take and for that I check, I am through. You see that? It reduces the problem. Yeah? Right? Okay. A similar thing you have seen earlier somewhere also. I am sure these are all MSc students, so you should learn in complex analysis. Okay. What I have learned? Suppose U is a disk. Okay. If you know that word, since it's a topology course, I have not talked about connected sets. Okay, I am using. Otherwise, assume this is U is a disk of the kind B A R or B Z not R. Okay, or R is positive, right? And suppose F and G are analytic functions, analytic or what I call holomorphic. Functions, right? Again, if I want to check F equal to G, there is what is called the identity theorem, which says let us look at the set of points Z in U so that F is equal to GZ. Okay, and assume, call this is E if you want. Okay, so E, this is a subset of U, right? Assume that, okay, there exists Z0 in U, so that Z0 is a cluster point, cluster or accumulation. Usually among many people you will use the word limit, but I don't use that word. If suppose it's a cluster point of E, so this set E has a cluster point inside U. You understand that? Then F equal to G. You see that? I don't have to check Fz equal to Gz for each and every Z in the open set U, in the open disk U. I only have to check, okay, look at the set of points. For example, suppose I have a Zn, a sequence, okay, in U, and such as Zns are distinct, and let us assume Zn converges to Z, then Z will be a cluster point for the set Zn. And assume that F of Zn equal to G of Zn for all n. Okay, then F must be equal to G. Yeah, so you see that there are lots of such uniqueness theorem across various branches of mathematics. Coming to algebra, you know that suppose I have two polynomials P and Q over a field. Okay, I will start again with the so assume or real field, right? Then when do I say P equal to Q, right? You know that. Okay, in algebra you must have defined, right? Now this says suppose there exists, okay, suppose let n equal to maximum of degree of P and maximum of degree of Q plus 1. Okay, take the maximum of these two degrees and plus 1, and suppose P there, okay, P of, let us say, alpha equal to Q of alpha for n plus 1 distinct alphas. Okay, then P, the polynomials P equal to alpha, and P and Q are the same, right? For example, for analysis, if I think of P and Q as polynomial functions, they are continuous functions. I want to check P equal to Q, then even the simplest case is would have been check that P and Q agree on a dense subset or rational numbers, etc. Whereas this is just because they are not only continuous functions, they are something extra. Namely, they are polynomials. In that case, to check these two functions are same, it's enough if we check they take the same values at n plus 1 point. What is n? Maximum of the degrees of P and Q. You see that all of them are related. Mathematics is beautiful if you stop to think and learn properly, rather than only I will learn only with a narrow way. Okay, pause, see. So that's point number 1 I wanted to do. Now what is point number 2? Point number 2, okay, How does, okay, this is the second fact. Okay, we had already seen if D is dense in X and D is a subset of E, then E is dense, right? Therefore, in particular, if A and B are dense in X, then A union B is dense. But natural question is whether intersection, that's very obvious, A intersection B. Let us start with R. My A is Q and my B is Q complement, that is rationals. Then A, both are dense, but their intersection is empty, therefore it's not dense. Right? These are all, as I said, these are all trivial observations, examples, okay, exercises. I shouldn't be spending so much time possibly, but I will do that. And the third thing, suppose I know D1, okay, let us say A in X and B in Y are dense. X and Y are topological spaces, A and B are subsets of X and Y respectively, and they are dense subsets. Then, do you remember we had already defined in our examples how to define a topology on X cross Y, right? What are the simplest open sets? Simplest open sets are the form U times V. And what is U? U is open in tau of X. This is open in Y. Okay, right. These are the simplest open sets, right? Okay. Now, let's look at A times B. This is a subset of X cross Y. So, what is the question you would like to ask? Very easy, right? I would like to know whether this is dense in the product topology. Okay, but that's again easy. Remember, as I said, it's to check density. It's enough if we check for basic open sets. Okay, right. Suppose I start with U cross B. Okay, a non-empty basic open set. In X times Y, right? Now this is non-empty, therefore U is not empty and V is also non-empty. So these are all non-empty open sets in X and Y respectively. Now A is dense in X, therefore there exists A in U intersection A, and similarly there exists a B in B intersection. Do you agree with that? Because these are non-empty open sets and A is dense in X and B is dense in Y. Now isn't it obvious? What is the point I should look for? What I have to prove? I have to prove A times B cross U times V is not empty. But I have to prove a point. That means I have to find a point AB here. Therefore, A must be in A, B must be in B, but AB must be in U cross B. That is, A must be in U and B must be in B. That means my A must be in A intersection U and B must be in B intersection V. That's all we found out. Therefore, you follow that? Yeah. What is the, okay? So what have you proved? If A is dense in X and B is dense in Y, then A cross B or A times B is dense in X times Y in the product topology. What is the next question I should ask? Yeah. Next question I should ask is the following. Suppose D in X cross Y is dense, right? Yeah. Now I can look at the projection map. Let us say pi x from X times Y to X. In that when we talked about continuous maps, we had already shown these are all continuous maps. We know that projection maps are continuous, right? Similarly pi y, right? Now I can look at pi x of D, call it D1, call it A perhaps. Okay, this is a subset of X. So I would like to know whether A is dense in X. That's the question. Okay, right? But that's easy. Right? So to show that A is dense in X, what does it mean? You are going to give me U, a non-empty open set in X, right? Then I have to show U intersection A is not empty, right? Now u is an open set, right, in x, and pi x from x times y to x is continuous, right? Now I have to make use of the fact D is dense in x cross y. That means I have to think of an open set in x cross y and show that it does not intersect, sorry, it does intersect D. Can you think of an open set? I'm sure all of you know that. Look at pi x inverse of u. And this we had already seen. This is set of, this is a subset u cross y, because xy belong to this if and only if x belong to u, there is no condition on y, therefore it is times y. Okay, if you have not checked all these things, please check. Okay, so this is a basic open set. Okay, this is an open set because pi x is continuous, but even otherwise it's a continuous set. Do you understand that? Sorry, it's an open set because u is open, y is open, therefore u times y is a basic open set according to our definition. Therefore this is an open set. Now D must intersect, right? This is not empty. That means there exists an x comma y here, right? In particular, x comma y, where does it belong to? It belongs to D, and x comma y belong to u cross y. That means, yeah, okay, x must belong to pi x of D, right? What is pi x of x comma y? That is x, right? Pi x of x comma y is x. Do you understand that? Yeah, therefore it belongs to A, which is pi x of D, right? And x comma y also belongs to u cross y. Yeah, xy belong to u times y. That means x belong to u. Therefore, okay, my x, which is pi x of x comma y, that belong to pi x of, that is my A. Yeah, and this x comma y is an element of D. You understand that? And this belong to this as well as it belong to the section. Yeah, are you following? Yeah, you understood, right? Pi x of x comma y is x, therefore x belong to A, and x also belong to u, therefore x belong to A intersection u, right? But what is this x? It is pi x of D. Therefore I have proved, okay, what I have proved, pi x of D is dense in, okay. But if you go through this proof, you will see it's actually yields a lot more. Suppose f from x to y continuous and plus onto, and D in x is dense. Then I want to say fd, let me call it A, fa, call it B, is dense in y. To show B is dense in y, what do I have to do? Start with the V, non-empty open set, right? Then I have to show y intersection, sorry, V intersection B is not empty, right? Okay, now let's see that. Now you gave me a V open in y, and I know D is dense in x. That means I have to get hold of an open set in x and use the fact A intersect that open set, right? So as I argued in the last thing, what will be my choice of u? Take f inverse of v. Since f is continuous, v is open, this is open. In where? In x. Maybe it's empty. Yeah, but it cannot be empty. Why? We started with V non-empty open set, therefore there is at least one y in V. And let's recall, what did I assume about f? F is on 2. Therefore there exists at least one x in capital X, such that y equal to fx. You understand? Therefore that x belong to, therefore fx belong to V, that means x belong to u. therefore U is non-empty open. Do you agree with that? So this is the place where we needed the fact that F is onto. Okay, therefore U is non-empty open set, and therefore U intersection A is not empty since A is dense in X. This implies there exists an X in U intersection A, right? That means in particular X belong to U and X belong to A. And what does it mean to say X belong to U? That means Fx belong to V, and yeah, what did I want to show? Yeah, Fx belong to V, and I have to show something about B. Yeah, right. Fx belong to V, since X belong to A implies Fx belong to A, right? So yeah, X belong to U, that means Fx belong to V. X belong to A, that means Fx belong to A. That means Fx belong to V intersection A, right? But where was X? X was in D, or X was in A. Therefore Fx is, I'm sorry, Fx belong to, getting confused. What did I want to show? I want to show B intersection P is not empty, right? Okay, so what have I got? Yeah, right. Okay, f of A is my B. Correct. Okay, sorry, f of, this way, see, I'm in a hurry, so I'm making mistake. That Fx belong to Fa. That is B. Therefore Fx belong to B intersection, right? Therefore I have next in here, therefore Fx belong to Fa, right? That is your B, and Fx belong to V, therefore V intersection B is not empty. This implies my B is dense in Y. Okay, please go through this. This is a very simple thing. Okay, for a moment I lost my focus, attention, so I got confused. Where I should have written Fx belong to Fa. I wrote it belong to A. That was the mistake. Okay, after that is everything is clear. Okay, so pause, review, proceed. I think that's about it. Let me just check whether I wanted to say anything more. I think that's it. So let us stop here. So as I said, these are all very easy facts which are left as exercises, but some of you know who are a little weak or scared of topology, I thought I wanted to make you very strong and confident. That's why I did all these easy things also. Okay, but you can see they may be easy, but one has to keep the focus. Okay, as I told the young, even I lost my focus. I had a little problem. Yeah, so okay, stay tuned, we'll meet again. I hope all of you enjoyed. Take care, stay safe, bye.